Welcome, everybody. It is my great pleasure to have this opportunity to introduce to you today's speaker, Professor Licia Verde. Licia got her PhD from the University of Edinburgh in the UK, working with Professor Heavens. Then she moved to Princeton University in the US with Chandra and Spitzer fellowships, many fellowships. She was one of the key members in the WMAP, Wilkins Microwave Anisotropy Probe, WMAP science team. Then afterwards, she joined the faculty at the University of Pennsylvania in 2003, I believe. And in 2007, she moved back to Europe to join the Catalan Institute for Research and Advanced Studies, ICREA, where she is now. Professor Verde's research spanned a wide range of field in theoretical and observational cosmology. And in particular, she has made a great impact on our understanding of cosmic microwave background anisotropies, galaxy clustering, and the primordial non-Gaussianity. And her research has been recognized by numerous awards and prizes. To just name a few, she has received the 2012 Gruber Prize in Cosmology and 2018, the Breakthrough Prize in Fundamental Physics. You know, I can continue for a long time. Without further ado, let's please welcome Professor Verde.
Thank you. So thank you for this introduction. Now that I got all red and all possible color, let's start the talk. It's a pleasure to be here. You know, after 2 years of remote stuff. Now we are doing some hybrid things, but it's a pleasure to be here in person. And what I would like to talk to you about is some recent effort that has been going on in my group, and some things that I started thinking. And the title I gave is Model-agnostic analysis, a large scale structure and implication for cosmology. And in other context, I would have said model independent instead of model agnostic. So let's just leave it for the question what that is and whether there is a difference in that. So it seems a little bit weird and not right, sort of to starting having fun doing science again when there is a whole lot of things going on in the world. But let's just keep on doing this. And this is my outline. First, I've introduced the context and a sort of introduction of the idea. Then I will tell you what keeps me up at night, again, in quotes. Then I will go on into a technical part, and which will cover blinding and model-independent analysis. And I know that the audience is very varied. So there are some of you who are world experts in some of these things, and some of you who know about cosmology and have seen the development of this field from outside. So there will be some equation and some technical bit, but if you're not aficionados, just ignore the equation and just get the meaning of it. If you're aficionados, we can dive into the equations too. And then I'll conclude. So let's start. I think we all know that cosmology has an extremely successful model. It's the standard cosmological model, and this model describes basically, grosso modo, all the observations we have of the universe from the earliest possible observation we can make down to very recent time, and a whole suite of scales ranging where different kind of physics it's important. And since the early year 2000, we have been talking about precision cosmology, because in these models, which is the Lambda CDM model, the standard cosmological model, has just 6 numbers. And with these 6 numbers, which are known with astonishing precision by now, we can describe a lot of properties of the universe. There are parameters describing the homogeneous backgrounds. There are a couple of parameters describing the perturbations. Of course, this leaves some open questions, which is what is lambda, what is cold dark matter, and what's the origin of the perturbation. So it's a wonderful model, but never mind that the model is very weird, because as we all know, there's a lot of it in the universe, in this cosmic pie that we don't know what it is. And I would like to mention something here, that this cosmic pie is the up-to-date one, but look at the date. The date is Planck 2013. Now, yes, true, there has been Planck 2018, there has been further analysis, but this hasn't changed much. So I like to recall that the COBE results were around 1992, 1994. 1992, they had the results, but they weren't published until a couple of years later. And then the first WMAP result came up in 2003, and then the first Planck result in 2013. So basically every decade we had a major advancement in cosmic microwave background data and analysis, etc. Now we are in 2022, and there's no CMB mission plan. Well, there are cosmic microwave background experiments on the ground. But this is because the information content that comes from the primary temperature anisotropy of the cosmic microwave background has been saturated. The next frontier is polarization, but polarization, you first do it from the ground, and only if you can show that you can't do what you need to do from the ground, it makes sense to try to go into space. So in this gap, so it was the golden epoch for cosmic microwave background experiment, and now is the golden era for large scale structure. And indeed, there's been an explosion of large scale structure survey and an explosion of what we learn about cosmology from galaxy and large scale structure survey. So cosmology is special in terms of what we call experimental sciences, because despite we say it's experimental, we can't make experiment and we only make observations. And we have to use the entire universe basically as a detector, but the detector is given. We can't tinker with it as you would tinker with any other experimental science. And this is Jim Peeble saying that, starting saying that decades ago. So the fact that you use the universe as a detector means that if you want to learn something, you want to make the detector as big as possible, and that you can't do experiment, you can only observe, has driven a massive experimental effort to observe as much as possible. And indeed, Planck is an example of what I call ultimate experiment. You have seen all there is to see of the primary temperature anisotropy of the cosmic microwave background. If you repeat the experiment, you're not going to improve much. Well, you can improve if you look at spectral distortion, you can improve if you look at polarization, but that will be a slightly different things that you're looking at. And so this is somewhat a mixed blessing. So the curse of cosmology is that since you only have an observable universe and you can only make observation, not experiment, then what we do mostly, we fit models that is constraining numerical value of parameters to the observation, and therefore almost any statement we do in cosmology ends up being model dependent. And then there is the astrophysics, which is complex astrophysics that is highly nonlinear and hard to model, that gets into the way. This is also a blessing because we can observe all there is to see, and so go and observe. And then you've done it. So this lambda CDM model, which started becoming precision in the early year 2000, has survived unscathed an avalanche of data. So on one side, there is the first CFA strip with the famous stickman. This was in the early 90s. And the lambda CDM model was sort of being established, at least the CDM. The lambda was still among the options back then. And then here, it's a representation of the BOSS, which is one of the reincarnation of the Sloan Digital Sky Survey, where that thing will be in a corner here, in a corner here in the yellow, somewhere in here, yet the model hasn't drastically changed, it still fits. So this has led some very senior and very famous people in the field to say, well, maybe we live in a maximally boring universe. And I would say that boring is good. Boring is good because cosmology is this science that is sort of halfway between the infinitely big and the infinitely small, where you can try to learn something from the infinitely big about the infinitely small and vice versa. So the fact that it's a boring universe means that you can do precision tests of fundamental physics by looking up at the sky with cosmological data. And so that is why we attempt, by looking at the sky, to address questions like what is dark matter, what is dark energy, what is the nature of gravity, what's the physics of the early universe, what's the mass of the neutrinos, and so on and so forth. It is because it is a boring universe. So boring is good. So let me go back to this observe all you can observe. So galaxy redshift surveys have been increasing about a factor of 10 every 10 years. And I know everything looks linear in a log-log plot, but bear with me. Years versus log of the number of galaxies. And here it's the history of the surveys. And a survey that has been going on for about a year, and I'm part of it, there are other people here who are also part of it, is DESI, which in the next slide I'm going to tell you exactly what it is, but the target of DESI is to get 30 million galaxies. And I'd like to report that when I was doing my PhD thesis, I was doing my PhD thesis on this survey here, which is the 2-degree field galaxy redshift survey, some 200,000 galaxies, and it took years for the survey to finish, and it was a 5 years effort and observing and everybody teaming and pulling and all so forth. So 3 nights of this, it's all of this. So this tells you the sort of the exponential expansion. And of course, there's more than that. There's Euclid, which more of you know, LSST, SKA, etc., etc. And so if we keep on going, all linear modes will be mapped by 2043, and all detectable galaxies will be mapped by 2061. That's, you know, that's an extrapolation. Doesn't mean that it's going to happen. And so even visually, that's the latest results that we have for larger scale structure survey come from the eBOS collaboration, which is not even 2 years ago. And even visually, the difference between the BOS, which was the previous survey that ended in 2014, although it took a couple of years more to actually get the final data release, it's here, and this is the eBOS. The eBOS include BOS, but extends it in this gap here, and it goes gaps between redshift 1 and 2, and the number density of the low redshift object become much higher. So the next one is going to be the DESI, Dark Energy Spectroscopy Instrument Survey. And for a summary, it's the Mayall 4-meter telescope at Kitt Peak. The Sloan was a 2.5-meter telescope. It's not anything particularly fancy yet. Look what it did. It's for the aficionado, a stage 4 dark energy measurement. Mostly the driving science case is baryon acoustic oscillation. For those of you who don't know what it is, I'm going to explain to you in a minute. 30 million spectra over 11 billion years of cosmic history and 14,000 square degrees. So that's more or less what that is. And my group member that I told you in DESI are Hetal Girmarin, who is a postdoc, Samuel Bryden, who is a finishing graduate student, Emanuele Fondi, who is starting graduate student. So what are baryon acoustic oscillation? I'm sure we're all conscious of the fact that we learn a lot about cosmology from the cosmic microwave background, and in particular from this pattern of acoustic peaks in the cosmic microwave background. Those acoustic peaks are oscillation of the photon-baryon fluid. So the photons and the baryon were coupled. There were perturbation and they were oscillating. And then at some point, when the photon and baryons decouple, then the photon stream through, and that's the image we see in the cosmic microwave background. And then the baryons are not supported by these oscillations, and therefore they start collapsing into the gravitational potential well. Good. So this was extremely useful information. This is, you know, the fundamental modes and overtones and all that jazz. But baryons are coupled to the dark matter, and I'm not saying anything crazy here. The coupling is gravity. And so if baryons are 1/6 of the dark matter, this oscillation leave an imprint into the dark matter distribution. And then this dark matter scaffolding remains there and then structure form and baryons light up on this dark matter scaffolding, and therefore carry this initial fingerprint of these baryonic acoustic oscillations. And so one should be able to see the same kind of fundamental modes and overtones that we've seen in the cosmic microwave background in the large scale structure, but at much lower amplitude and a much lower signal to noise because of this. And so this is a standard ruler. Well, actually it's in 3D because it's a standard length. So I would say maybe it's a standard bubble, and this is going to be important for a moment, but okay, I think you know what I mean. And the fact becomes a classic Alko-Paczynski test, something that was not done in the cosmic microwave background, because in the cosmic microwave background, we only see 2 dimensions, and the cosmic microwave background, it's basically one screen at a given time. But in the large scale structure, we see the 3rd dimension, the line of sight, and we see the clustering of several different redshifts, so we can do sort of evolution or tomography, if you want, of it. So let's recap. The baryon acoustic oscillation are a standard ruler, and the physics of the sound wave in the early universe propagate until radiation and matter decouple. This imprints a scale, which is a key observable, is useful for geometrical test, dark energy, equation of state, evolution of the scale factor. And it's the early universe physics, which assume it's well known, that sets it. So cosmic microwave background and early universe physics in a lambda CDM model constrain the standard ruler range to 0.2%. That's precision cosmology. Now, of course, if you take the lambda CDM early time physics and throw it out of the window, then the standard ruler is not constrained at well. And what could actually really change the determination of the early time standard ruler? Well, if you have, for example, some kind of dark radiation, or if you change when photon and baryon decouple, or if you change the rate of the early time expansion history, then you mess up what you believe is the standard ruler. So, okay, so in the large scale structure, we expect to see this imprint of the standard ruler. So if you do a correlation function, and this is a little bit exaggerated, you expect to see a spike, and then if you say, okay, then let me take out the broadband, then these spikes will look something like this, and then you can measure it. And conversely, in Fourier space, then you will have a power spectrum, and then you will see this fundamental modes and overtone as was seen in the cosmic microwave background. But what's going on here? So first, the standard ruler can be observed both along the line of sight and across the line of sight. So the plane of the sky and along. But hang on a second, we measure redshift and we want the distances. And so this is the classic Alko-Paczynski test. If you have the wrong conversion, a signal that is supposed to be isotropic is not going to look isotropic. So this is the standard Alko-Paczynski test. Therefore, you can measure clustering along the line of sight and perpendicular to the line of sight. And then you can say, what is the deviation, which is the parameter alpha, that I get of this peak along the line of sight and across the line of sight? Are they two the same? If I have the right model, that alpha is 1, both along the line of sight and across. If I don't have the right model, it's not 1 for both of them. So keep in mind this alpha, because we're going to come back to this alpha in a moment. And again, we measure redshift at angles, but we need distances. And the moment you measure redshift and you want a distance, you already assume a model. So even before we say we compress and into our data into a power spectrum or a correlation function to interpret it, we already assume a model. So there's more than that. There is also redshift space distortion that tells us information about the growth of structure. How does it work? Well, if the universe is not homogeneous, there are peculiar velocities, so there are deviations from the Hubble flow. And this deviation distort the galaxy map along the line of sight. So this seems a distortion and seems a bad thing, until you think that, but this distortion is actually driven by gravity and the matter in homogeneity and the matter over density and under density, which is actually an interesting information to extract and to interpret. So it turns out that in the linear regime, this distortion depends on this combination, which is basically related to the linear growth rate. And then in a lambda CDM type model, it can be written in something like that. And also in GR type model can be written with something like that with a different value of gamma. If you become crazy about non-GR model, then it becomes something else. Okay, so here we are. This is a mock simulated survey. If you could measure distance, it would look like this, but you don't. You measure redshift, you interpret redshift as distances, so it looks something like that. It's distorted. And actually, you will realize if you are in an underdense, if you are in a underdense region or in an overdense region, how the actual deviation from the Hubble flow will go, and it will, so if this is linear and non-linear, an overdensity will look like this, and an underdensity will look like this, and in the linear flow. So, and you can see it here, right? This is the non-linear elongation along the line of sight, and the fact that this wall look like bigger wall, this is squashing on linear scales. The very first plot that I saw visualizing this come from the early year 2000 from the 2DF field, and it's the famous Barthel-Frey plot for the correlation function. If the clustering was like this, statistically homogeneous and statistically isotropic, this isodensity contour, this is along the line of sight, and this is across the line of sight. This black line will look circles, but they don't. So this is the nonlinear regime, and this squashing here compared to here is the linear regime. That squashing is what tells you the linear growth rate of structure. And so what has been done since the early year 2000 is to repeat this at a larger scale, where you have many more linear mode and many less messing around of nonlinearity, and do that as a function of redshift. And so this comes from the BOSS 2013, that's the main galaxy sample. And this is the eBOSS, where you can do it in different samples up to between redshift 0 and, well, 0, 0 you can't, say 0.2 to 1.6. Yeah, you need another bit of information because before we can go into the details, which is reconstruction. It's a sort of time machine or magic until wrinkle cream. So we say that the baryon acoustic oscillation is this pressure wave from the initial perturbation that travels until the coupling and then stays there. So initially, this looks like a sharp peak, and it's isotropic around the initial perturbation. But then, as the universe evolves and becomes a little bit nonlinear, this sphere, say, become distorted and become distorted. But then you say, haha, what actually sources this distortion? Well, it's the underdensity and overdensity that are around it, which I can estimate. And then I can reconstruct for the aficionado with this kind of equation, the displacement field, and then move the particle back and relinearize the signal. You can't do it perfectly, but it's much better than that, and therefore sharpen the peak. And so that's very useful to sort of re-extract better information. So physical information that one can extract from a larger scale structure, but there's a lot. The clustering tells us, back to the initial questions, what's dark matter, what's inflation, what's the neutrino mass, etc. The standard ruler, the geometry, tells us about what the expansion history of the universe and therefore the nature of dark energy. The redshift space distortion tells us about how structure form within the background, so has information about the nature of gravity and what makes this perturbation grow. On larger scales, one can ask things about homogeneity, primordial non-Gaussianity, and of course, each of these little dots, it's a very rich information, it's got an entire spectrum, And therefore, there's other, not necessarily cosmological information in the spectral analysis, which may be a key to ensure robustness of everything else. Yes, you can also do the same with the Lyman alpha forest, but I'm not going to talk about that here. But let's go back to our issue before. I think it goes deeper than that. I like Daniel Kahneman about theories. He says, we can't live in a state of perpetual doubt, so we make up the best story possible and we live as if the story were true. And in cosmology and in the standard cosmological model, there's a lot of these stories. There is GR, there is the Big Bang, there is the choice of metric, there is nucleosynthesis, and you keep on going and going and going. So cosmology tends to rely heavily on models, both for the signal and for the noise. And we know that essentially all models are wrong. Some of them are useful, but essentially all of them are not perfect. So this is in the back of my mind. So I started at the beginning say boring is good because we can now test the model and we can learn about dark matter and dark energy or neutrinos. But how do you test the model? If the very first thing you do when you get your data, it's just to use a model to interpret them. Isn't this a little bit of a, circular argument? And can you do without? So Feynman says, the first principle is you must not fool yourself and you are the easiest person to fool. So there are some recent efforts that have been done in-house to actually address this. And here is a summary. So first, I want to discuss the blinding strategy for spectroscopic clustering surveys that was published in Blind Watcher of the Sky. So there are 4 authors in the paper, Samuel, Bryden, Hector Gilmarin, me, and Jose Luis Bernal, who was a student and now move on to greener pastures. And so here are the 3 DESI members at the DESI meeting, blind and unblind in themselves. And then a way of actually doing model-independent analysis of galaxy clustering. There's 3 papers out and more in the pipeline. So let's talk about blinding and blind analysis. There is a nice article in Nature back in 2015 about blinding and how to use blinding in physics and also in astro and in cosmology. So the idea is, again, you want to hide the truth to make sure that you don't fool yourself, that since you expect the result, you actually keep tweaking until you get the result that you expect. So why do we want to blind? I think we can summarize this in this quote. Although each experiment was honestly made, they were, except for the first, conducted in light of previous results. The question of when to stop the search for sources of error is very important. And I just put those plots here, which are the value of the Hubble constant as a function of time, to just illustrate my point. So there are several ways to blind in large-scale structure, but few have been applied. In supernova, they do blinding. In gravitational waves, they do blinding. In particle physics, they do blinding. They do it in a sort of different way than it's suitable for large-scale structure. In large-scale structure, we haven't done that a lot, almost nothing. The classic technique, like salting, salting means injecting a false signal, are not really applicable because the signal is statistic anyway. You can do it at the summary statistic level, or you can do it at the inference at the likelihood level, or you can hide the data among a set of mock data and then do all the analysis there. But we were thinking, can you do it at the catalog level? Let's see if we can. So a priori, the catalog level blinding allow you for infinite freedom to modify the field, like you can even write whatever you want if you modify the catalog level. But what makes sense and how to blind just for cosmology, not for systematic or anything else? So what do we want ideally? Let's recap how the workflow of getting the data, from getting the data to getting the cosmology works. So here your telescope, get the data, do the redshift pipeline, get the raw catalog, do it the systematic way to get the full catalog. You check always with cosmology performance, whether that's okay. If it's not, you go back until you are happy. When you are happy, Then you say, yes, let's give the catalog to the collaboration. That's the internal release. And then everybody started doing baryonic acoustic oscillation, resonance-based distortions, keep looking at them. If they find something that doesn't work, they go back and say, hey, you did something wrong here, reanalyze it. And then this check is always done with cosmology, with the comparison with the lambda CDM model. And then when you have agreement with the lambda CDM model, then you get your cosmological results. And then, hey, you publish the paper. There's something not quite satisfying there. So that's what you want to do. First, you want all the checks here to be non-cosmology performance, and that's fine. That's not a big deal. But then what you want to do, you want to put this into a blinding box. There's a random seed that goes in there, and you blind your catalog. Then you give it to the collaboration. The collaboration knows that it's not necessarily expected to find the lambda CDM because you mess around with it. So you do all their analysis, they get the blinded results, they can check whatever they want through the results until they are happy. When they are happy, they say, okay, we are happy. Now we freeze the pipeline and we unblind. And the main way of unblinding would have to be this. You simply unblind, so you go back and look at the original catalog, you do the clustering analysis, and then you get the cosmological results. Ideally, it would be great if you could simply correct the results you had directly from the posterior and get the cosmological results. Start writing the papers. So at least you know more or less what you are getting. Decide whether you send it to Nature or whether you send it to APJ. Say. And then meantime, you actually redo the actual MCMC and everything on the unblinded catalog just to get it right. Can we do that? And what are we going to put in that box? So the suggestion for blinding at the catalog level is to act only along the line of sight. Because so you don't mess up with the angular weights, it's not easy to blind accidentally, just move only along the line of sight. And then blind both the baryon acoustic oscillation and the Redshift space distortion signal by applying and combining two types of shifts. One is a geometrical Alko-Paczynski-like shift, and another one is a density-dependent Redshift space distortion-like shift. Let's look at them. And here is where there's something for the aficionado there, and my words are for the non-aficionados. So usually, when you go from redshift to distances, you pick a fiducial model, and then you transform those redshift in distances, and then you distribute your catalog to the collaboration with the fiducial model and with the distances. What I say is we do the following. I get a fiducial model, I go from redshift to distances, I correct that fiducial model for a change, a small change in the parameters, and then I convert those distances into redshifts. And then I shipped to the collaboration the corrected redshift and the fiducial model without this extra correction. So I mess around with you between the comparison between distance and redshift. Now you take the redshift, you use the fiducial model, not the fiducial corrected, and so you get wrong distances. But I haven't done anything strange there, because if my fiducial model was different from the true underlying model, it would have been exactly the same at all, for all purposes. The nice thing is that you can write down analytically what's going to happen to your clustering because of I've been diabolic here and I've corrected my suite of cosmological parameters in the redshift to distance correction. And then you can write down even what is the ratio blinded to fiducial of anything that you're going to get out, which is the alpha and the D. On the redshift space like distortion blinding, you know that the redshift space distortion already distort the line of light signal, but the magnitude is driven by this F parameter, which is unknown. So let's mess up with this in a controlled way. So you know that for reconstruction, you're already doing this step. You are reconstructing the field and you applying a distortion, but remember when I show you that circle, you apply this de-wrinkling along all direction. So let's mess around with that de-wrinkling only along the line of sight by correcting it by an amount that I don't tell you what it is. And then I ship it back to the collaboration. And now I can compute exactly analytically what you're gonna get when you try to measure the F parameter. And I can even make you believe in GR modification. I can even split the dysfunction history from the growth history. But you say, aha, below the smoothing scale, you're not doing anything, right? Above the smoothing scale, you're doing that. Below the smoothing scale, where you reconstruct. And so that's a really good question, because the smoothing scale is going to be given by the number density of objects, so there will be a trade-off between noise that this kind of thing introduces and the return you get in actually blinding your result. But it's something that you can test extensively on simulation. And if you want to see how it looks, this is the reconstructed real space density. This is the original Redshift space density. And that's the blinded Redshift space grid. These are the displacement highly enhanced, so you can see them. So the difference is tiny, but the survey is big, and there's a lot of statistics there. So this is enough to actually send you completely off track if you're trying to reinterpret this, but in a controlled way. So that's what we did. And let's see what happened. So this is the application to the BOSS data after having applied on a whole suite of simulation to make sure that the signal to noise is under control, you don't add extra noise, etc., etc. So this is after reconstruction, and this is the analysis which is called full shape, which is the combination of baryon acoustic oscillation and Redshift space distortion. You need to do that, and that is without reconstruction. So the blind catalog gives you the red one. The corrected one, which is, since I know analytically what I've done, when I am blind, I can simply shift directly the posterior. I don't have to rerun the analysis in principle. Give me the black one. And the original one on the actual original catalog, now that's unblind by construction, is the blue one. So the black one allows you to start writing the papers already. Right, while everything runs, and then you finalize the plot with the real one, which is an advantage in terms of time. So let me give you a summary of the blinding results. We've tested the scheme on a suite of mocks and on BOSS data to validate that blinding does not significantly change the error bars. Because in principle, if you blind and then you get error bar that are very different from the error bar you will get on the survey, it's a little bit useless, right? It doesn't matter, because at the end you reanalyze the real survey. But if your error bars, instead of being tiny, becomes huge, then there's no point. And the analytic results agree with the refitted results, which speeds up the last stage of the analysis, which is the one that stresses you most usually, right? It's the 90-90 rule. You think the last 10% is going to take you 10% of the time, and the last 10% is going to take you 90% of the time. And for information, it's all in there. So the type of question that I always get when I talk about blinding is, when do you unblind? What about effective field theory of large scale structure? Do you blind within lambda CDM or away from lambda CDM? What about primordial non-Gaussianity? And what about non-zero neutrino masses? And I'm going to leave this as an inspiration for the question and answer session. And I'm going to move on to the other thing I want to talk about, which is model independent versus model dependent interpretation of galaxy clustering. And here it's, again, the three papers that I was talking about. So let me take a step back and talk about compression. If you get given a survey like this, let's imagine this is your survey, the number of numbers you need to specify that is at least the number of galaxies times 3. You want X, Y, and Z for each of those objects. That's a lot of numbers. So you can do a compression. And the first compression you do is you compute the power spectrum. So this compression will be lossless if the field was Gaussian. If the field is non-Gaussian, which it is, the compression is not lossless, but it's okay because you believe you lose not too relevant information, or at least information that is not that easy to interpret, so you do it anyway. Then you say, but this is not isotropic because I have Redshift space distortions. So your power spectra become 3 power spectra, become monopole, quadrupole, and hexadecapole with respect to the line of sight. And that's a compression which is If you're willing to use a power spectrum and compress at that level, it's basically lossless. You lose a little bit of nonlinearity, but you lost more nonlinearity already. So. And this brings it down from the number of galaxies times 3 to few tens of numbers. And then what we've been discussing so far is to further compress this into 2 numbers, which has the 2 alphas along the line of sight and plane of the sky, and the squashing of this butterfly plot, line of sight with respect to plane of the sky in the linear regime. So we went down for a given effective redshift of the survey, or a given slicing redshift, from n gal times 3 to 3. We're bound to have lost some information by doing that. What have we lost? So here it is. These are the plots that I showed you before. You do the DAO, you have the standard ruler. Remember, if you don't want to calibrate the standard ruler at early time, you can still do baryonic acoustic oscillation. You just get relative expansion history and not absolute expansion history. But let me stress here, you can't measure H0 from a galaxy redshift survey alone unless you assume the length of the standard ruler, because all you measure are redshifts and angles. There's no way you can measure H0 from redshift and angles. You need to assume a standard ruler, or you need to assume something, and then you measure H0. If that comes from the early time physics, you're assuming early time physics. If you want to drop the assumption about early time physics, then you don't get H0. You can't have the cake and eat it, right? And then you do the redshift space distortion, compress all this information in another number, which is F or F sigma 8 for the aficionados. But that's not the only way to analyze a galaxy survey, right? There's a different philosophy, which is do like the CMB. What do you do in the CMB? You pick a model and you run your MCMC through that model. Then you pick another model and you run the MCMC through that model. You don't take and say the height of the first peak, the width, where I move the first peak, the ratio between the first peak and the second peak. That we were doing before WMAP. When WMAP came along, it became obvious that doing it that way was suboptimal. So you pick a model for the anisotropic power spectrum and go on. So approach number 1 is said to be more model independent, because you extract sort of the physical information which does not depend on the model, constrain physical quantity, not parameters of the model. You constrain the parameter of the model a posteriori. Approach 2 is more computationally expensive, of course. You have to run a different one for each choice of model, but gives better constraints. How much better constraints? Let's look at them. So this is our in-house test of these 2 approaches. This is just the BOSS DR12. So that's just the redshift space distortion in a projection, omega called dark matter H squared and H. That's the redshift space distortion, just BAO, the redshift space distortion, and the full modeling fit, which is done like an AFT of LSS. So obviously, look, the blue contour are much tighter than the orange contour. Okay. And then you ask, what the heck is the star? And the star is my way of saying what's going on. So let's pick this model here. Let's pick this model there. Plot the prediction compared with the data and see where the difference lies. Here it is. So in terms of compressed variable, F sigma 8 and the 2 alphas, that's the data for BOSS DR12. The 2 models fit equally well. But when you go to the actual multiples, there's a difference there. And the difference is all on large scales. On small scales, both models fit exactly the same way. So what's going on there? And could one extend the model 1 to match the statistical power of model 2 in a simpler way? Conserving a speed up, which is a factor between 30 and 60, depending how you do the analysis, and be model independent. Well, it turns out that the difference in information content between approach 1 and approach 2 is mostly the behavior of the matter transfer function at the turnaround. That is the detail of the expansion history around matter radiation equality. to a smaller extent is the amplitude of the BAO oscillations. Let's keep this in mind. And it turns out that if you visualize that, different changes in parameter, changes in omega matter, in omega baryon, in H, in NS, in sigma 8, and even in the neutrino masses, they all look like something like this, except the neutrino masses, it's much suppressed, but all the other ones sort of look something like that. And so what do we say? We say, how about we compress all this in the slope of this function here? And now this is a phenomenological parameter. I can measure it from the data. And then every theory will give me what the prediction is for that phenomenological parameter. So I can write it down in terms of the theory. It's basically how the transfer function responds to change into things that affect the matter radiation, the transition around matter radiation equality. So let's say we add an extra effective parameter to the usual compressed variable, physical parameters. And it turns out that this is quite generic. So it mops up a lot of the information like FNL, neutrino mass, dark radiation, generic histories. It mops up a lot of that. All right, the proof of the padding is in it. Here it is. The analysis again from Boss, DR12, CMAS, so I give you one redshift only. So this is the analysis, the classic BAO plus redshift space distortion. That's the standard results of the collaboration, are the black one. Now, what this approach, we call it shape fit, this extra phenomenological parameter, here it is this M. And now this tells me nothing about what you want to know. What's omega matter, what's omega baryon, and things like that. And then I have to convert this within a model to constrain on the cosmological parameters. And I can do that. This is done with a BBN prior, with Ben consistency prior on omega baryon, and assuming lambda CDM, and you get the green. And what's the blue? The blue is the EFT of Laurent's crystal. So there's good agreement, of course, it's the same survey. But the error bars are not drastically different. So this is effectively a lossless compression. I say it with an asterisk because I had to assume a BBN prior. If I don't assume a BBN prior, then the green one gets a little bit bigger than the blue one. And the difference is from the height of the baryon acoustic oscillation. So if you trust that your model can describe the amplitude of the baryonic acoustic oscillation, there is another 20%, a little bit of information there. But I would argue that that information is not too clean, because you can easily imagine bias schemes that mess the amplitude of the BAO around. And you can easily imagine that if you don't know your nonlinearity too well, you're going to mess up with the height of the BAO.
But so this only is only true within lambdas. Yeah.
So this is not, but this, to go from here to here, I need to assume a model. So this, in this plot, is done with lambda CDM. Then we've done it for anything that changed the expansion, the background expansion history, and that holds perfectly well for obvious reason. And then we did it with FNL, we did it with neutrino masses, and it still works very well.
But you could cook up a model where it doesn't. Right?
You could cook up a model where it doesn't. That's true. I haven't been able to yet. I try. We're trying, so that's why some of the papers are still coming out.
I can give you one if you just suppress the small scales.
Yes. Yes. If you suppress the small scales, that's true. So the thing is, how much do you trust your nonlinear modeling of the small scales? But anyway, I'm not saying that anything is wrong. I'm just saying that for doing it that way, you have to assume a model from the very beginning and then carry all the analysis through. You can't just be agnostic from the very beginning.
Sorry. Mm-hmm. Could you quickly repeat what is the efficiency gain between the two, in a sense?
You mean in terms of timing?
Yeah.
So it depends how you do the analysis and how many extra parameters you put. You marginalize it over ER summation, you don't, what you do with the various biasing model and things like that, between 30 and 60.
Okay.
So what does it do? All right, so let's look at it again. This is two ways to see the same thing. So basically, let's look at this plot. This is the omega matter H, and this is the length of the standard ruler. What the slope only tell you, it gives you a handle on the shape of, it gives you a handle on the standard ruler, but the handle come from matter radiation equality, from the shape of the transfer function. It doesn't come from CMB in fair quantities. So then after that, and so the idea is that any model will have a prediction for alphas, the squashing, and the slope at the larger scales. Any model will have prediction for that. Now, whether that compression is lossless for every model, that's not obvious. But every model will have predictions for that. And so then, after that, we felt good enough to actually enter the PT challenge. So what is the PT challenge? The PT challenge is this collaboration. Takahiro Nishimichi and collaborators did a high-resolution suites of huge boxes and body runs, made it public, but did not say what the underlying parameters were. And they just say, let's see who can recover them. They are there. Go be my guest. And so we also entered the Hall of Fame. These are all the other collaborators that enter, and we are down here. So this is blind. So all, you see, everything is reported in terms of delta parameter over parameter. So it's still blind, even in the published paper. But once you do the analysis and you enter it, then Takahiro will send you an email with the actual parameters. So then you can do those plots in terms of delta with respect to what you find in the original and then do the plot. And actually, Samuel video himself the moment he was unblinding. So you can actually see his result and then erase the part of the video when he mentioned the value of the parameter to keep it blind, and you can see the video there. But let's remind ourselves that the total volume is 10 times bigger of the future survey, not of the present survey. It's 2 orders of magnitude bigger than the present survey, is an order of magnitude bigger than the future survey. So really, this is, and this is the result of the PT challenge. So you want to hit within your error bar the cross of those lines, that's 0, because it means no bias. And this is shape fit within an assumption of lambda CDM, because if you have different redshift, the relation of this quantity across redshift depends on the model you assume. And this is the comparison with the EFT. So in this sense, and again, there is some difference because of what you do with the omega baryon. How do you put the prior on omega baryon and how much information you are willing to extract from the amplitude of the behavior. So I would say that it passed with flying colors. It's true that there may be tiny little bias here, right? And a posteriori we figure out where that is coming from, but now it's not blind anymore, so we don't present it. But remember, the volume is 10 times the one of forthcoming survey, and there's no marginalization over survey systematic and things like that. So whatever residual biases you may have, it's completely negligible. So I think I really need to try to finish. I would say that accuracy is the new precision, and accuracy means both doing the analysis, making sure there are no systematic, but also if you want to test the model, you can't put the model in and then find the model back again. That's definitely not accurate. That may be precision, but it's not accuracy. And so In the first paper of the series, 1/3 of the paper pages, including references and abstract, is about systematic tests and cross-checks. In the second paper of the series, about half of the paper pages, again including references and abstract, is about systematic tests. In the next paper on the EBOS data, there's more systematic checks pages than everything else. So that's what I mean when you really need to go beyond the spherical cow. The control of systematics is important. And just to tease you, this is the EBOS analysis that is ongoing. We're now with the extra challenge of including reconstruction, because the official analysis takes the BAO information from the reconstruction and the ratio space distortion from the non-reconstructed field and combine them optimally. So this can be done in the classical analysis, but we need to generalize to shapefit. And so we'll be presenting that too. And this is a teaser to show you. These are 3 official analyses by the collaboration. This is in real space, and these 2 are in Fourier space, but they are done with slightly different assumptions, slightly different modeling, slightly different way to use the systematics, and so on and so forth. And this is shapefit. So we don't know which one of these 3 or 4 is completely correct, but whatever it's there that may be wrong, it's not expected to really sway you completely, because the 3 different approaches are really consistent with each other. But this is the extra information that shapefit tell you. So then from here, you can go and do a whole suite of models. Any dark energy model you want, you don't have to rerun, you just compare as a post-processing with this. Even FNL model, we show that it's very well described by this. So before I finish, I really need to finish. It's at least 30 times faster than full modeling approaches. It's model independent, I would say rather model agnostic, because you still put some reconstruction there. Reconstruction assumes GR on small scales, but scales that are so small that it's really Newton. So, I mean, yeah, you can mess around with that too. And it naturally splits early time and late time variables. M is a early time variable, everything else is a late time variable. So if you are one of the fans of solving the Hubble tension by saying there is a mismatch between early time physics and late time physics, you want to keep them separate to figure out if that's the case, and that allows you to actually keep them separate. And it naturally enables better control of systematics. So it turns out that the systematic weights, due to the fact that you have different scene, you have different sampling in different parts of the sky, different galactic contamination, different number of stars that come in the middle, etc. And this goes into systematic weights. So what we did the analysis twice with the systematic weights on and off, just to quantify, how much would the systematic weight really change. So the alphas and the F sigma 8 are not really affected, but all the systematic weight effect is mopped up by M. So if you find that M tells you you have some primordial non-Gaussianity, you want to have done your blinding correctly, so that you know that is not the systematic weights doing that, but you know that it's gonna affect M, but it's not gonna affect anything. And the other thing that really surprised us a lot was ER resummation. So this EFT theory, they need to put this ER resummation in, and it's something that needs to be calibrated on simulation, marginalized over, etc. Shapefit doesn't put ER resummation, doesn't need it, because it looks very large scale and linear scale. But with or without ER resummation, then you would get a difference. And this difference comes basically from leakage of that across all scales. So one got to be a little bit careful of saying this is a nonlinear effect, and it's not going to be important. So conclusions. Concordant vanilla lambda CDM model still rules, but there are some puzzles that remain, the famous H0 tension, the sigma 8 tension, and that's why blinding, I think it's important. there is a coordinated effort to move from precision cosmology to accurate cosmology, and the field has moved beyond the spherical cow and pie in the sky type of analysis. But I think that model agnostic or model independent approaches are really much needed, especially if we want to test the model itself with this data. And I thank you for your attention. I stop here and I leave you with this. Thank you.
Thank you very much. A very nice talk. So now we have questions, and maybe if you could just repeat a short this way the audience
Yes.
can get. So questions? Go ahead.
Sorry. I have a question regarding what you showed in the beginning with the blinding.
Yes.
So you showed that plot, and I was just wondering that plot with the H0 tension and how this developed over the years.
Yes.
And I was just wondering, since to my knowledge Planck was always blinded, is this a hidden critique against, for example, shoes?
No. It's simply an example to look historically. The H0 started by 500 and then it came down very slowly. And obviously either the error bar were bigger than the error bar that have been published, or there were many studies out there that were finding different values, but the author kept going like, nah, it's so far away from what's, let's not publish, let's keep checking. So it's not a criticism to anybody in particular. It's more like a criticism to our psychology.
But they do not blind, right?
So some H0 analysis do blind. I don't know in particular shoes, what they do, because there are so many steps in there that I don't know which one they are blind and which one they are not. But for example, the time delay lengthening, they do blind. So, and at some point they were joking before unblinding and say, when do we publish the paper? Now we freeze. And when we do the analysis, when do we not publish the paper? And so they agree. If H0 comes out negative, we don't publish, and we go back. Otherwise, whatever we get, we publish. So no, it is not. But the Planck was not blind, right? Planck was blind in the sense that the error bar were so small that effectively is blind compared to all the previous. But it was not blind. And I don't know if anybody's thinking about how to blind the CMB analysis. That would be an interesting. I guess you would do it from the likelihood, because it's so complicated and everything is degenerate with everything else, and it depends so much on what you do in the likelihood that you could easily blind it at the covariance or likelihood level. Yes.
Yeah, thanks. I was thinking, looking at the EBOS results that you showed, and you had as a function of redshift, the parameters that you're interested in.
Yes, F sigma.
And what I didn't quite understand now in this last part of your talk, where you're using the slope, this bench, whether one could have a similar kind of parameter to describe tomography.
Exactly.
Is that something that...
Exactly. So in the EBOS paper that is coming along, there will be an M as a function of redshift. So you take the big survey, you cut it in redshift samples, and for each sample you have an M. And then you say, well, in a lambda CDM, M should be constant with redshift. But in a FNL model, M should not, because the bias evolves across redshift, and therefore, and the FNL signature evolves as a function of redshift. So I should expect a drift on M. What do I see? But I can't,
there might be other things, right?
Yes, exactly.
Another kind of phenomenological parameter that you could introduce.
Yes, exactly. And could you introduce another phenomenological parameters? Yes, we explore about having two M's, but current data are not good enough to allow to break the degeneracy between these two m's, and therefore you end up with a degeneracy, and then you want to collapse it back into a single parameter. But you could. Yeah.
And I have just one follow-up question. Could you address a little bit the blinding in the lensing case? I don't know if that's...
Okay, so there are two types of lensing we are talking about. There is the weak lensing and there is the time delay lensing. So I don't know the time delay lensing. So what the weak lensing they did, as far as I know, they did blind at the level of summary statistics, or they did blind at the level of shear, like putting a sort of an offset in the shear. Now, if you remember in the DES paper, at some point they don't use one of the samples, they had a high redshift, because with the blinding, it was not consistent with everything else, and therefore they decided to exclude it. And then in the final analysis, since it was excluded before, they couldn't introduce it. So that is a very important sort of programmatic question to ask yourself. When you start blinding and you have different samples and different probes, do you blind them in a coherent way? So then when you do a joint analysis, they all give you the same answer. Of course, within the blinded model, which you don't know what it is. Right? Or do you blind them independently and just go with it? Can you even blind them in a coherent way? So blinding at the catalog level for clustering, you can do it in a coherent way because you are taking the catalog. Of course, if the catalog becomes very sparse, a very high redshift, then you got to be careful because maybe your setup introduces some noise, so you may have to do some trade-off. But say you combine Lyman alpha and clustering, and then you blind the galaxy cluster and you don't blind the Lyman alpha, when you do the cross correlation, you're going to find strange things. So either you blind both, or you decide that you're just going to live with it. And you know that you're going to find inconsistency because you know one is blind and one is not blind. But it's a programmatic decision, the discussion to take at the very beginning. Or say, I do a joint analysis with the CMB now. Do I also blind the CMB or I don't? Or what do I do? Yeah.
All right. I have a question about this parameter M.
Mm-hmm.
And you've shown a plot where changing many different if I understood correctly, changing many different cosmological parameters all tend to give similar slopes.
Yes.
In this M.
Yes.
And I want to ask if there's sort of a reason
yes.
for this,
yes.
and if this M corresponds to some
yes.
sort of feature
exactly.
in the universe.
Exactly.
Or...
So for those of you who read, I don't know if you read the famous or infamous BBKS paper, the one that actually first tells you, so it tells you a lot of things, but it's famous because of the matter transfer function. So there they introduce, in the appendix. So then they introduce a parameter, big gamma. And big gamma basically say, we know the transfer function at very large scale is got to be 1. But then at some point, around the scale of matter radiation equality, then the transfer function bends and then give the characteristic shape to the power spectrum that we observe. Where does that bend happen? And what's the sharpness of that bend, basically? So what are the details of matter radiation equality and when does it happen? And so that was big gamma. And big gamma in a lambda CDM model is basically omega matter H. But away from a lambda CDM model, you still have a gamma, but it's not just omega matter H. So what M does, it basically say, let me capture this gamma in terms of the slope of the transfer function between where it's 1 and before you start having the baryon acoustic oscillation, where if I measure the slope, I'm going to measure something which is a complicated combination between the transfer function and the baryon acoustic oscillation. So they say something about the evolution of the universe around matter radiation equality.
Is there a reason, or is it a happy coincidence that many different changes all correspond to similar slopes?
I think there is a reason.
Right.
and so not necessarily a similar slope, but a similar shape. So you take the shape and then the slope will change, but the shape is more or less the same. And then you have only one parameter, which is the slope of that shape. The reason being is that when we think in terms of cosmological parameters, we think in terms of numbers in that model. But what we measure is the physical effect on the observables of those parameters. So if you can capture the physical effect of the observable from the data, then different parameters sort of are degenerate. It's somehow like, say, I measure gravity acceleration just by dropping things. And then I construct different models of gravity. How can it be that all these different models of gravity, they hold these parameters, but then somehow they end up giving something which is the gravitational acceleration at a given scale or whatever. And it's because that's what you can measure when you do an experiment. You don't measure the parameters. The parameters are our creation. The universe doesn't know about the cosmological parameter, but the universe knows about the physics at play and how the observable respond to that physics. So I know it's a philosophical answer, but...
Thanks.
Do we have other questions?
So you mentioned neutrino masses, but then you didn't talk about that. Does the blinding help you in any way? Does it tell you something interesting about the constraints of neutrino masses?
Okay, so so we know how to blind for the two Alcopachisky parameter and for the F sigma 8. And then we know how to blind for everything that affect the larger scales. And the neutrino do affect the matter radiation equality because they are also changed between relativistic and non-relativistic, so they change that. So if we want to blind for neutrino masses, we haven't done that yet. So we've wrote down how to do it and how to blind for FNL too. We've wrote down how to do it, but we haven't done it yet, and that's what the student needs to do before he can defend his thesis. So it's got the carrot and the stick. But you could do it, probably not by displacing particles. You would have to do it by weights, and you can imagine why that is, because if you think the halo bias, the scale-dependent halo bias, FNL, it's basically a weight. You don't do it by moving things around. And so the same way we can probably do it for neutrino masses. So our priority was to blind for whatever DESI is the key results, the key project, whatever they promised to the funding agency. And then the next step is things that we want to do anyway, but we haven't promised the funding agency. Can we blind that too, and to what extent? So I think we can do it. We've wrote it down, but between theory and practice, we really need to test it on massive simulation and make sure that it does. What we know is that on real non-Gaussian simulation, M mops up the FNL very well. What we don't know is if we can blind for it from a real catalog.
Great, I think we're good, and we're right on time. So let's thank our speaker again.
Thank you.